Welcome to the Organic Chemistry video content to accompany the Organic Chemistry 1 lecture guide and the Organic Chemistry 1 primer. These problems come from Part 2, dealing with substitution, elimination, and oxidation reactions. Our first problem deals with defining nucleophilicity and basicity. A simplified way to think of nucleophilicity is that it is a measure of how rapidly a species donates electrons to an electrophilic site. The nucleophilicity is related to the energy of activation for that electron donation step. A smaller energy of activation for electron donation corresponds to a better nucleophile. Basicity, on the other hand, is a measure of the extent to which the conjugate acid of a species is favored thermodynamically. The more thermodynamically favored the conjugate acid side of an equilibrium is, the stronger the base will be. Given those definitions, if we would like to use a kinetic study or a study of the rates of reactions to determine a property, we would have to use that study to determine nucleophilicity. On the other hand, if we had a study of an equilibrium process, which is a thermodynamic study, we would determine the basicity of a species using such an analysis. Now, with these definitions in mind, we are asked first to rank a series of species in terms of their nucleophilicity, and then to rank some other species in terms of their basicity. In order to rank the nucleophilicity, we need to know the nucleophilicity trends. And if we take a look at these species, we can see right away that one of these species is neutral while the others are charged species. A neutral species will generally be a much poorer nucleophile than are the charged species, so we can go ahead and rank that species as the fourth or least nucleophilic. Next, we may notice that we have a very bulky substituent on this negatively charged atom, the nucleophilic site, whereas you have just a small non-bulky chain on these other two nucleophilic oxygen and nitrogen atoms. Remember that the bulky sites hinder the approach of the nucleophile to an electrophilic site, which makes it a very poor nucleophile. So that may be our next worst nucleophile. Perhaps it would even be the worst nucleophile in some circumstances. Now, these other two we have are different in that one of them has a negative charge on an oxygen, one on a nitrogen. The oxygen is more electronegative, and it's more difficult to pull the electrons away from it. Therefore, it is not as nucleophilic as the negatively charged nitrogen in this species. So we'd rank this as number 1. If we take a look at the same species and try to rank them in terms of basicity, we would say that the least stable of these would be the most basic. The least stable of these would be the species with a negative charge on the nitrogen. So that would be our strongest base. The electronegativity of the oxygens with negative charges make them more stable than a minus charge on a less electronegative nitrogen atom. The most stable of these, of course, will be the neutral species, which does not have an excess of negative charge localized on one atom. So how do we differentiate these negatively charged oxygen atoms? It might help to draw in the lone pairs and to realize that these non-bonding pairs will have repulsion with branches nearby in a destabilizing repulsive inductive effect. So this is our second strongest base, and that leaves, by process of elimination, this other species as the third strongest base. And now we're going to transition from discussing nucleophilicity and basicity to discussing substitution mechanisms that we learn in later lessons. First, we'll have a problem about the SN1 mechanism. In this problem, it states that an SN1 reaction occurs when 2-bromo-2-methylpropane is heated in water. And we are simply asked to provide a reasonable arrow-pushing mechanism for this reaction and to label the final neutral organic product that we would isolate if we did this reaction. We first have to realize that the SN1 mechanism is defined as the sequence of two of our elementary reaction steps, heterolysis followed by coordination. The heterolysis step must occur with the release of a good leaving group or a stable anion. Generally, fluoride or something more stable could conceivably be a leaving group for such a reaction. After that heterolysis step, we have a carbocation and a bromide anion. Now we have to do the coordination, and that's where the other reactant, the water, comes in. A lone pair on a water-oxygen will be attracted towards that positive charge with attendant release of a proton from that oxygen. The net result of this coordination is the formation of an alcohol and a proton, and this will be our final neutral organic product isolated from the reaction. Our next problem involves a closer analysis of just the first step of an SN1 mechanism. This is asking us to show just the thermally induced heterolysis for each of these four compounds, and remembering that once a carbocation forms, it does have the potential to undergo a spontaneous carbocation rearrangement if in doing so you obtain a more thermodynamically stable species. Our halogens, the bromine, chlorine, and iodine, are all good leaving groups because if they come off, they will form relatively stable anions. After release of the most stable anion through the heterolysis process, we should have these cations as shown here. The second part of this problem is asking us to assess whether there will be a carbocation rearrangement that would be spontaneous, such that the majority of molecules in the sample would undergo such a rearrangement prior to a subsequent step. Prior to making such an analysis, it is sometimes helpful to fill in the hydrogen atoms, at least on the cationic site, and the sites adjacent to the initial carbocationic site to which the positive charge may rearrange. And these hydrogens are shown in green on our diagram. In order for a carbocation rearrangement to be spontaneous and thermodynamically favorable, it will have to involve the formation of a more stable cation, so the movement of a positive charge to a more substituted site. So I've labeled in red the different sites adjacent to the initial carbocation. If we take a look at these, in the first case, the secondary carbocation only has the possibility of rearranging to another secondary or primary position. It won't gain any great stability by doing either of those processes, so you will not have an overwhelmingly favorable carbocation rearrangement. In the second case, you start off secondary and the two potential rearrangement sites are secondary. In the third case, however, we start with a secondary carbocation and there is a tertiary site adjacent to it. So if we take the two electrons that are in this carbon-hydrogen bond and move them over to this site, we will leave a tertiary carbocation, and that would be spontaneously formed, leading to this carbocation that would be present prior to any subsequent steps with other molecules. In the rightmost case on this page, we see a secondary carbocation. It certainly won't rearrange to any great extent to the less stable primary site, but if we take one of these methyl groups and utilize those two electrons to move over to give a fourth bond to the carbon on the right, the initial carbocationic site, we will form a tertiary carbocation that will look like this. And this cation, likewise, as in the third case, will form very rapidly. Most of the sample will go to this prior to interaction of the carbocation with a separate species to undergo another step of reaction. So now we've seen some SN1 reactions. We know that you have to do a heterolysis to form a carbocation. We know that some carbocations may rearrange. We'll have to check for that anytime we do an SN1 reaction. And we know how the coordination works to make the final product. So here we're asked to predict the major products of the reaction shown on this page. The first step in the SN1 reaction will be heterolysis. So if we consider the first case, we would do a heterolysis to form this secondary carbocation with release of the bromide as the leaving group. This is a secondary carbocation. The sites adjacent to it are primary and secondary. There would be no overwhelming drive for this secondary carbocation to rearrange prior to the coordination step. So our other reactant, the water, will undergo a coordination with that carbocationic species. You could draw the release of the proton in that step as well, and you'd be left with a neutral alcohol as your product. Notice that this coordination step starts with an achiral carbocation, and you've generated a stereocenter. Remember that in those cases, you will always get a racemic mixture, so that exactly 50% of our compound product will be the R isomer and half will be the S isomer. In our second example, we have this alkyl chloride. We'll have heterolysis of the chloride leaving group, leaving a carbocation, and the chloride leaving group here. And in this case, if we look at the adjacent sites to the carbocationic carbon, we see a primary site and a tertiary site. The initial carbocation formed a secondary. So we should move something from this tertiary carbon. We'll have to check and see which thing will move. We have a proton and we have these two CH3 groups. Generally, your proton will be the easier thing to move. It's smaller. So that is a thermodynamically favorable and spontaneous carbocation rearrangement. Only then will you have a coordination of your other reagent. In this case, it's methanol. The coordination of methanol to this carbocation mechanistically will mirror just like what we saw up here for the water. You'll have donation of a lone pair. You'll need to lose a proton from the methanol in order to maintain the neutrality of the oxygen. And you will have this ether as your final neutral organic product. This is an achiral product, so we do not have to worry about whether we have racemic mixture or... In addition to simply predicting the products of SN1 reactions, we may have cases where we are asked to predict the relative rates of the SN1 reactions. The slow step, the rate limiting step of an SN1 reaction is the heterolysis, because that is the step that forms the least stable of the species along the SN1 pathway. If we compare these two reactions, we only have to think about that particular step. In the first case, we form a tertiary carbocation. In the second reaction choice, we form a secondary carbocation. The tertiary carbocation is much more stable. It is formed much more quickly, so this will be a faster reaction. Now, how about this case where the heterolysis leads to the formation of a secondary carbocation in both cases? You have, in fact, the exact same carbocation formed. Well, the difference in this case is the leaving group. In one case you have the bromide, in one case you have the chloride. Well, bromine is a larger atom than is chloride. As a result, the formation of the bromide is more favorable. It will not require as high an activation barrier to release it from the carbon, and this is going to be your faster reaction. Now we move on to some questions about the SN2 mechanism. In this case, we're told that an SN2 reaction occurs when 1-bromopropane is heated with sodium hydroxide. We are asked to provide a reasonable arrow-pushing mechanism for this reaction and to label the final neutral organic product. The first thing we have to do is recognize that the sodium hydroxide is an ionic species. So in a solvent in which it is soluble, you'd expect some dissociation into the sodium and hydroxide. The hydroxide is a good nucleophile, and so that will serve as your nucleophile for the SN2 reaction, which is a concerted step leading to the formation of the alcohol. And that is your final neutral organic product. Here we are given two pairs of reactions and we're asked which of the pair would react faster by an SN2 pathway. In the first case, the only difference is that we have a tertiary alkyl bromide for the first reaction and a secondary alkyl bromide for the second reaction. The SN2 reaction gets slower the more branches are present at the reaction site, because those branches will slow and hinder the approach of a nucleophile. In fact, we learned that a tertiary reaction site will not undergo an SN2 reaction for an alkyl halide at any appreciable rate. So that's very slow. The secondary sites, while considerably slower than a primary site for the SN2 reaction, will still be fast enough with this alkyl bromide to be a reasonable reaction, and certainly considerably faster than any reaction at the tertiary site. If we consider the pair at the bottom of the slide, we see that the substrate is the same. We have the same secondary alkyl bromide in each case. The difference is the reactant, the thing we are attempting to use as the nucleophile. The SN2 reaction requires a good nucleophile, and this species is ionic because you have a metal, non-metal attached to one another with the oxygen and the sodium, so you'll form a good nucleophile in this case. This is in contrast to the neutral alcohol that will not dissociate into ions here. That will not even do an SN2 reaction at any appreciable rate. So our second reaction is certainly the faster of the pair. If we take a look at a couple additional pairs of reactions, and again consider which is faster by the SN2 pathway, now we have a case where both of these substrates, the alkyl halides, are the same, both of the nucleophiles are the same, and what we've changed is the solvent. In one case we have a polar protic solvent, a hydrogen bonding solvent, and in the second case we have a polar aprotic solvent. We know that a polar protic solvent is capable of hydrogen bonding, which will lead to a weakening of the nucleophile strength. SN2 reactions are faster when your nucleophile is stronger, and this hydroxide nucleophile in this case will be stronger in the polar aprotic solvent. In the final case, we have identical substrates in terms of the number of branches. It's not like this first case on the first page where we had a tertiary versus a secondary. But there is a difference in the leaving group. The leaving group does have to come off in the course of the SN2 reaction mechanism in the concerted step. So the more stable that leaving group is, the faster the reaction will be. Our nucleophile is the same, so that we can't use that to differentiate in this case. And this bromide is a bigger anion, a much more stable anion, so that will lead to an easier, quicker formation of the product in the case where the leaving group is bromide. The more stable the anionic leaving group, the faster the SN2 reaction rate will be. Next, we are posed with a question involving a reaction of a chiral alkyl bromide, the R2-bromobutane, with sodium acetate. And that species is drawn out in a condensed formula. So we've got to set up our reaction, figure out what all these species look like. I start by drawing the R2-bromobutane. There are a variety of ways you could have drawn it. I've drawn it as shown here, and I've indicated the priorities. First priority bromide, second priority is the ethyl group, and third priority is the methyl, with your lowest priority group pointed in the back. So we have set up our R2-bromobutane. And if we draw out the Lewis structure of this condensed formula for the sodium acetate, it will look like this. Of course, we have a sodium-oxygen bond, so in a solution they would be expected to dissociate into the sodium cation and the acetate anion. The anionic part will serve as the nucleophile for this reaction. We would expect the negatively charged site to donate electrons to that carbon with release of the bromide leaving group. Remember that the SN2 reaction undergoes Walden inversion, or inversion of configuration. So if we start off with the R configuration, we will end up with the S configuration of the product. In this case, the acetate will then be pointed in the opposite direction of the leaving group that it displaced. So I've drawn on this hashed line, and we would have the S isomer of this product. Part of the question asks us to provide the structure of the transition state to help illustrate the origin of this observed stereochemistry, and the transition state is some species that lies part of the way in between the starting material and the product. So it's attempting to illustrate that while this acetate nucleophile is starting to donate electrons to that carbon, and you're starting to break the bond to the bromide, you're starting to push some negative charge into the bromide. This shows you that there is something in between where these substituents were initially pointing down, and you're going to push them so they're up, inverted the opposite direction. And this is a typical transition state like that you see in your lecture guide or primer.